All right, we are solving problem number 3 from week 2. Let's read the problem. It says two friends, Drew and Barry, decide to exercise by running along a 5,000-meter long track. Drew runs half of that distance at 2.75 meters per second and walks the rest of the way at 1.75 meters per second. Barry, on the other hand, spends half of his time running at 2.75 meters per second and the other half of his time walking at 1.75 meters per second. Which one reaches the end of the track first? So let's focus on a few of the important things over here. Both of them are running the same track, so 5,000 meters long, 5 kilometers, except Drew splits up as two different speeds. See, both of them run at two different speeds, right? Both of them run faster in the beginning and slower at the end, and it's the same speeds, 2.75 meters per second and 1.75 meters per second. Drew runs half of the distance at the fast speed and the other half at the slow speed. Barry runs half of his time at the faster speed and half of his time at the slower speed. See, it might seem like they're doing the same thing at first glance, but they are not. Okay, this is not the simplest of problems. It sounds a bit complicated. Let's see how we would approach it. As you know, we have this nice problem-solving rubric that you'll be graded on, and you can use the rubric as a guide on how to approach a problem. So how do we approach problems? First step is sketching. The first step to solving a word problem is to visualize and make sense of the physical information you've been given. And since, again, I can't read your mind yet, I would like you to show me what you're visualizing in your head. I'm going to look at if you're visualizing the problem correctly, if you interpreted the problem correctly. So one of the easiest ways to do that is to make a sketch of the situation described. A good sketch should contain all of the physical information contained in the problem, both explicit and implied. If your sketch is done well, you should not need to look at the text of the problem again after completing it. That's a good point to keep in mind. How do you know when your sketch is done? Well, if you never need to look back at the word problem again, the sketch should have all the information you need. So let's go back and do a sketch. Zoomed in too much. There you go. Okay, let's do a sketch. We have a track. So this is our track. We could say this as the starting point, 0 meters, this as the ending point, 5,000 meters long. Let me follow my own convention. I'm gonna make Drew always be red. I'm gonna make Barry always be green. So Drew runs half this distance, so let me mark half the distance, and that would be 2,500, nope, not 25,000, 2,500 meters. So Drew is running, yeah, that's my running man. That looks horrible. How do I draw a person running? There you go. He's running fast. At a velocity, let's call that V1. There's going to be a bunch of velocities, that's why I'm labeling it V1. At 2.75 meters per second. But for the second half of the trip, the last 2,500 meters, he is walking casually. So no longer running. And I will represent his velocity with a vector, and just to keep consistent, I made a long vector for 2.75 meters per second. I'm making a shorter vector for this 1.75 meters per second that he runs at for the second half. Okay. Let's see what the other part. Barry. Now, Barry's thing is not related to distance. Barry's thing is related to time. So maybe we need to get some time labels in here. Let's draw Barry. Again, for the first half of the journey in terms of time taken, Barry's running. Let's get him some running legs. Yeah, Barry's running, and again, at larger velocity of, well, we could just call this v1 because it's the same value, 2.75 meters per second. And for the second half in terms of time, Barry's just walking. Let's do v2 equals 1.75 meters per second. Now, how do we indicate that these are two different times? Well, we could say something like Barry takes a total time of, I don't know, some value. Delta t Barry is question mark. We don't know what that is. That's the total time Barry takes to complete the journey. So I could say this takes place for delta tb over 2, and the second speed takes place for delta tb over 2. Right, that's how I'm indicating. Well, since we added some time information over here, we could also say delta t drew to complete the journey. We don't know. The question is which one reaches the end of the track first. If we knew delta t d and delta t b, we could just compare them and solve our problem. Okay, I think that's a pretty good sketch. Our final goal is trying to get to these numbers so we can compare them. If we notice we ended up missing some sort of information in the sketch, we can always go back and add it. All right, let's see what our next step should be. Our next step is physics representations. Physicists use multiple representations to describe and understand phenomena. So representations are a bit more concrete than sketches. They are very specific kinds of figures or diagrams. They must be appropriate to the phenomenon being described, accurate, and most importantly, consistent with each other. If you end up with multiple representations, make sure one doesn't contradict the other. Common physics representations include graphs, force diagrams, motion diagrams, work energy bar charts. So I don't know, this is a motion-related problem. Most likely motion diagrams or graphs might be useful to us. Let's see what we can do. Well, my first thought might be like, hey, let me get a motion diagram going, but would a motion diagram really be useful in this case? I could do, more spaced out dots for the bigger speeds, less spaced out dots for the smaller speed, but at least for Drew, that's pretty easy because I know where the distance is, it's half and half. But with Barry's one, I can't really fill out a motion diagram because I don't know what those times are, and very hard to do. Motion diagram, we could go down that path. I don't think it's going to give me anything useful. I think the useful information is already in the sketch. But graphs, well, maybe graphs might be useful. Can we represent what's given to us in terms of a graph? So let's get a graph going. All right. Again, red is always Drew, and Barry is green. So Drew runs for half the distance at a certain speed and the other distance at a different speed. Well, then maybe we can draw a velocity versus distance graph, right? Like, we could say this distance, distance in meters. Well, this distance can be 5,000. I can mark a distance as 2,500. Velocity is in meters per second. And there are two velocities that we care about, right? There's the 2.75, and then there's another one, which is like 1.75 meters per second. And what would this look like? Let me draw a little bit of a dotted line over here. So for the first half of the distance, Drew is running at, so this is Drew. Drew is running at 2.75 meters per second. As soon as he reaches the halfway mark, he drops down and stays at a constant velocity of 1.75 meters per second. There you go. That is a much more concrete view of what's happening in the form of a graph. What about Barry? Could we draw a graph for Barry too? Give him a nice physics representation. Well, Barry's case, again, is related to time. So a velocity versus distance graph wouldn't be really useful, but his velocity changes with time. Again, don't forget the units. What did we call that ending time when he finishes his journey? We called that delta t Barry. We don't know what that is. The middle of that is delta t b over 2. And again, in shape, it's a very similar graph, but the axes mean completely different things. And I'm going to call this 2.75 meters per second, and this one 1.75 meters per second. For the first half of the time, faster. For the second half of the time, slower. There you go. Okay, representations look good. Now, what are we trying to get at? We're trying to get at those final total times taken. So let's work with Drew's. Well, it's a velocity distance graph. That's not something we see too often. It is useful in this case right now. Well, let's think of what our equations are. I know velocity is related to distance, as velocity is distance over time. Another way to write it is delta x over delta t. You know what, since I'm using x, why not actually make this as x? That way I'm consistent. Delta x looks nicer to me than distance. Okay, that's our equation. What can we do with that? Well, there are these two segments, right? We could figure out what the time is for segment 1. We could figure out what the time is for segment 2. Okay. This delta t1 plus delta t2 has to add up to delta t Drew. Barry. And before we move on, notice we've moved on to the next part of our rubric, consistent mathematical procedures. Mathematics is a tool commonly used by physicists to represent and understand physical phenomena. When using mathematical procedures to solve a problem, a physicist starts from general equations. Did I do that? Yeah, the speed related to distance and time, that's a very basic general equation. I didn't get to the complicated stuff immediately. Start from a general equation. And then we select a procedure that's likely to lead to a reasonable answer, and then we carry out that procedure. But while we do this mathematical procedure, and another important thing, the mathematical procedure should be consistent with our physics representations. Notice how I am not just doing the math out of nowhere, right? Part of my math is showing up in my physics representation. They should be related and consistent with each other. But another important thing, explanation of thought process. This is a physics class. Again, I can't read your mind yet. And until I do, one of the skills I want you to develop is a good thought process and expressing to me what that thought process is so I can see if you're going in the right direction. Physicists must always make sure that their work is understandable by those who read it. This means that when solving a problem, you should always explain your thought process. A complete explanation covers both what you did, so, what representations did you draw, what mathematical procedure you chose, and why you did what you did. This explanation should be very clear and easy for others to follow. So what I did and why I did it. So I feel like I missed out a little bit on that. I should give a little bit of an explanation over here. Drew's speed changes with distance. Therefore, I am drawing a velocity versus distance graph. Barry's velocity changes with time. Therefore, I am drawing a velocity versus time graph. See, there you go. The things I was saying out loud, well, again, I'm not watching you do the problem. I'm not probing your brain like Professor X while you're doing the problem. You have to show me your thought process. All right, let's go over here. What is my thought process over here? Just a little bit. The time taken for each part of the journey should add, man, my handwriting's bad, right? Should add up, no, maybe, shouldn't write then. Oh God, that's even worse. That's even worse. Let's see, there's a way to type things here. The time 24, there you go. The time take, the sum of the times taken for each part of the journey should add up to the total time for true. Then we can substitute in the generalized equation for each time segment. There you go. Now, if I'm grading this, I know exactly what your thoughts are and what you're doing. So let's see. This is my generalized equation, which tells me delta t can be written as delta x over the velocity. So delta t1 should be delta x1 divided by that v1. Delta t2 is, again, delta x1 because it's the same distance, this time divided by v2. And all of that will reach to delta td. Well, let's see what we have here. Delta x1, this was easy, 2,500 meters, right? Again, I'm reading from this graph over here. And for that 2,500 meters, Drew was moving at 2.75 meters per second. 2.75 meters per second plus another 2,500 meters divided by 1.75 meters per second, and that'll give me the total time. Let's get to crunching. 2,500, 2.75. I get 909.1, and what happens to the units? Well, the meters go away, and the second comes up over here. Plus what do I get over here? I'm getting 1428.6 seconds. Same thing, the meters cancel out. And if I add these together, plus 909.1, I'm getting approximately 2,338 seconds. It's 37.6, but you know, I don't need that kind of accuracy over here. And this is delta TD, the total time Drew takes. Total time Drew took to cross 5,000 meters. Okay, let's do the other half. Let's do Barry's thing. Ooh, that's not nice. Whoops. Okay. Let's get rid of that. Barry's one, well, we could take the exact same thing. We could say delta TB over 2 plus delta TB over 2 is delta TB. That's, again, very obvious. It is the same explanation over here as what we wrote on the left side. Now, how do we work with that? Well, we can substitute in our general equation, or, well, can we work with this? I don't know what these times are. What if I replace them with delta x1 over v1 plus delta x2, which is the different distance covered in the second half, by v2 equals delta dB. Well, I know this, I know this. I don't know what that first distance is. I don't know what that second distance is. So this is kind of a pickle, right? What do I do over here? Well, maybe this is the wrong approach to go over here. You know what? It's fine that I wrote this. As we said, you make mistakes and you learn. Same method as that one's Drew, right? Drew's doesn't. That's not how you spell doesn't, and I know that. D-O-E-S-N-T. Doesn't work. Same method as Drew's doesn't work here because I don't know x1, delta x1, or delta x2. Ooh, what do I do? And I don't know delta TB over 2 because I don't know delta TB. Well, maybe we can take a different approach. Different approach. I do know that each of the segments, each of those distances covered in each segment have to add up to be 5,000 meters, right? What if I call this delta x1, and what if I call this delta x2? So like the distance covered over here and the distance covered over here, delta x1 and delta x2. Well, now I can say delta x1 plus delta x2 equals to 5,000 meters, right? I don't know what delta x1 and 2 individually are, but I do know they have to add up to be 5,000 meters. Substitute general equation. Well, what can I do now? Let's see. How can I rewrite delta x1? Well, I can rewrite delta x1 as v1 times delta dB over 2, right? You run at the fast speed for that first half of the time plus v2 delta TB over 2 equals to 5,000 meters. Is this solvable? Yeah, I know V1. I know V2. I can solve for TB over 2. So let me do a little bit more algebra. I get V1 plus V2 times delta TB over 2 equals 5,000 meters. This is 2.75 meters per second plus 1.75 meters per second times delta TB. I'm moving the 2 over there, so I get 10,000 meters on this side. Well, delta TB is equal to 10,000 meters divided by, what's 2.75 plus 1.75? I get 4.5 meters per second. Well, these 2 meters can cancel, and I get 2,222.2, repeating, of course, seconds. And this is the total time Barry takes to run 5,000 meters, or to finish 5,000 meters. Okay, well, I think we're at where we want to be. We can compare. We can compare these two. Let's get a different color going over here. Therefore, wait, who wins? Oh, Barry takes a smaller amount of time than Drew to cross 5,000 meter. Ugh. Barry wins. Woo! Done. Problem solved. But are we done? No, we're not. We have one of the most important parts of problem solving still left. The jumping of monitors. Now, the evaluation of the solution. Physicists always use multiple methods to evaluate their work after reaching an answer. Evaluation provides a quick and easy way to gut check an answer to see if it is plausible. Like, why would I trust these numbers? 2,300 and something, 2,200 and something? Those are close enough. Like, is there some other way we can guarantee, like, oh yeah, no, I really thought that, Barry was going to win, and he did. As learners, you must explain how you evaluated your answers. This is one of the biggest parts if you're actually ever doing research in physics. Possible methods of evaluation include, and are not only these things, you can come up with your own stuff, but these are some examples. Limiting or special case analysis. Does your answer behave the way you believe it should when you change certain values or look at special cases? Unit analysis. Does the answer have the units you would expect it to? Physical reasonableness of answer. Does this answer make sense to you? Is it the correct order of magnitude? Like if you're finding the mass of a person and you end up getting like 3,000 kilograms. That's not reasonable, right? Even if like it just came out of your math. 2 independent methods. Well, maybe you can come up with a different way of solving this problem to give the same answer. Consistency of representations. Do independent representations agree on the answer you reached? If we had like, a motion diagram and a graph, we could maybe compare them and see if they matched up, or did the math match with the graph, something like that. So let's see what we can do over here. This is where it requires a little bit of clever thinking. Well, something... you know what? Let's use some of our calculus ideas. What do we call the area under a velocity versus time graph? That has physical meaning, right? So let me actually do my evaluation on the side over here. I can say something like, let me type this out. Come on, give me big letters. 36, yeah, there you go. Let me type it out. The area under a velocity versus time graph is the distance traveled. Okay, looking at, again, I forget who's Drew. Looking at Drew's V versus T graph, we see that the first chunk has a larger area than the second chunk. This tells us that Drew travels a larger distance at the faster speed of 2.75 meters per second, and a smaller distance at 1.75 meters per second. But on the other hand, Barry travels equal distances at 2.75 meters per second, and did I mix these people up? I did, didn't I? Yeah. See, now, how did I catch this mistake? Because I'm trying to write something here that in my head isn't matching what I wrote as my answer beforehand. So this should be Drew. Let me see. Let's get this out of the way. Total time Drew takes. Yep. Oh, come on. This is all confusing now. Okay, Barry is green, Drew is red. Where did I make a mistake? I made a mistake over here. Since method 1 was used as, since method used with Drew doesn't work here. Okay, so this is fine. So this was fine. This is Barry. This is Drew. Barry wins. Okay, I made the mistake over here. Looking at Barry's V versus T graph, we see the first chunk has a larger area than the second. This tells us that Barry travels a larger distance at 2.75 meters per second and a smaller distance at 1.75 meters per second. On the other hand, Drew, our red guy, Drew travels equal distances at 2.75 meters per second and at 1.75 meters per second. Well, what does this mean about average velocity? Well, this means that on average, Barry is traveling at a faster speed compared to Drew. Right? Does this make sense? Barry stays longer at 2.75 meters per second, and I can explain that at a faster speed since he stays longer at 2.75 meters per second compared to Drew. So Barry's average speed is higher. Since Barry's average speed is higher than Drew's, we expect Barry to win. And Barry did win. And That's what our math says. I like that. That's an intuitive thing. I didn't use math over here. I used kind of like a comparison in the graphs to figure this one out. I shouldn't just do one evaluation. I should definitely try to get a little bit more in. A simple one to do to supplement our bigger evaluation is unit analysis. We should definitely make sure the units worked out. And I already did that by working out the units inside my calculations. Time should have come out in seconds. My meters canceled out. The seconds got flipped over. So that's one evaluation. Number 2 evaluation. Calculation units work out as seen in the math. Time came out in seconds. Yeah, time came out in seconds after cancellations, which is basically what we wanted. So, just don't tell me like units work out without ever showing the work inside the math. And, tell me like, oh, I was expecting time to come out in seconds, and I did show that the time came out in seconds. All right, let's see how we did. Sketch. So you can always self-evaluate, self-grade before you hand in the problem. Solution does not include a sketch. Well, no, that's not it. Sketch is not relevant to the problem or not detailed enough. No physical quantities are labeled. The sketch is inaccurate. Well, the sketch is relevant. I drew and Barry and their speeds, and I put in physical quantities, and everything got labeled. Yeah, maybe we added a few extra labels later, but yeah, no, physical quantities and labels are all there, so it's not inadequate. We're getting there. The sketch is relevant but incomplete. It does not label all relevant physical quantities, nor does it include all the necessary states. Well, there aren't multiple states. When we do other chapters, there might be like a beginning and an end to a momentum problem. So you might have to do a initial state and a final state. So you have to have 2 sketches. Anything we missed over here? We marked delta t. Be consistent. We call this delta t1 and delta t2 when we did the math. And then when we dx1, we called both of these dx1. So let's call this dx1. We also called this dx1. So we almost missed a label. It's nice to have all the labels in the sketch so we know everything that we're talking about. Oh, something that's kind of ugly? We use delta x1 over and 2 over here too, even though those aren't the same distances. So let me actually label these delta x1 and delta x2, and I should get some different labels for this one. I'll call it delta x half, delta x half, right? Half the total distance. And I should change that over here to delta x half, delta x half. See, I made my math consistent with my sketch. I would have probably taken some points off right over here if I just handed it in the way it was without fixing the sketch. The sketch is now complete, and it identifies all the quantities that we used in our math. So, yay, adequate sketch. Physics representations. Let's see. The solution does not include relevant physics representations. Oh, I think we included 2 of them, and they were relevant. They had the information from the problem, so blah. Representations created are relevant, and the only problems, but they to the problem, but they have major errors or omissions. I don't know. My math matched up with this, so I don't think my graphs had errors in them. I even used one of the graphs to do an evaluation, so I think I can reasonably cancel this out. Representations created are relevant to the problem but have minor omissions or mistakes. Ooh, yeah, this is easy to do, right? Let's check if there are any minor mistakes. Did I label them? That's a mistake I always end up making. Drew velocity versus distance. So I'm drawing a velocity versus distance graph. Did I put the units in? I put the units in. I did some extra labeling over here, some extra markings. This one, I labeled it as a velocity versus time graph. And I think I put all my labels in. Could have been a bit neater, but I'm also using this new tablet thingy, so it'll get better. Yeah, I don't think there are any minor omissions or mistakes. Consistent mathematical procedures. Math procedure cannot be followed from the work shown. General equations used are not shown, only numbers or derived equations. No, I wrote down my big general equation. I did my algebra and stuff before just dumping numbers into the problem. If I just started with numbers over here, I would have gotten a low score on my math procedure. So it's definitely not this. Math is incorrect, inconsistent. Well, I can go double check. This is a good time to go double check all my numbers. Did I do it wrong? Did I do the procedure wrong? Again, I think not. I looked at it. Productive mathematical procedures are chosen, which are consistent with physics representation, easy to follow, but contain algebraic errors. So this is, again, reminding us, let's catch some errors over here. This wasn't an error, but remember I was going to do a different procedure that wasn't working. And you don't have to delete this or anything. You can just write like, hey, the previous method didn't work for this thing, so I'm going to do a different approach. Show me your thought process. Mistakes are not bad things. It shows growth and learning. But yeah, nothing incorrect in terms of algebra that I see. Answer reached has appropriate units. Consistent with physics representations. Yeah, definitely. I drew from my representations to do the math, free of errors, as far as I know. Answer reached has appropriate units. We definitely did that one. Explanation of thought process. Did I do explanations? Yeah, I absolutely did. So I can cancel that one. I think my explanation was pretty coherent. Explanation is slightly unclear, missing some minor information. Covers what was done, but not why it was done. Did we do what? Yeah, I said I'm drawing a v versus x graph. That's the what. And why did I do it? Because Drew speed changes with distance, right? So I need distance and speed. Yeah, so I think I did the what part. So the yellow is the what part. The green is the y part. And what did I do? I said I can substitute generalized equation for each time segment. Why did I do it? Well, because the sum of the times taken for each part should add up to the total time. That's why I did the times and put stuff in. Yeah, I think I did what and why. So yeah, shows physical and conceptual understanding. I think I have some physical understanding of this. Anyway, evaluation of solution. Well, we definitely tried an evaluation. Evaluation is incomplete. Only the unit is evaluated. We definitely evaluated the unit, but we did other stuff with it. Or an invalid conclusion was drawn. Almost drew an invalid conclusion because I was labeling everyone wrong, but came back and fixed that. Evaluation is appropriate, but vague or minor mistakes are there, or a clear conclusion about the reasonability of the result is not drawn. We had a very clear conclusion. Our, discussion over here clearly predicted that Barry is traveling at a faster average speed and should win the competition. So I think I'm going to go with valid conclusion about the reasonability. Now, is this the best evaluation? It could definitely be better. How could I make it better? Well, I could calculate the average speeds and make sure what I'm saying is right. But I'll leave that as an exercise for you to do, or, maybe I trust my ideas over here and I think it's clear enough. All right, that's how we do a problem. Well, I think I'm gonna get a 15 out of 15 in this one. Maybe I could put a little bit more effort into my evaluation. Maybe this becomes a 14 out of 15. I don't know. But this is how we do a problem. Please look at the rubric. The rubric isn't just a thing like that you have to do by memorization or rote. It's there to help you work through your thinking process, help you show us your thinking process in many different ways. All right. I'm going to stop the recording. See you all next time.